We're looking at intersection of two planes today. So a couple of possibilities. Planes don't intersect. Planes do intersect, and when they intersect, planes are going to intersect in a line. So where you get the intersection of two planes, that's not trivial, where they're not parallel or they're not coincident, we're expecting to get the equation of a line. Okay. Bit of a shout out to grade 10. Back when we did elimination of variables, we're going to play that same game with two planes. So here I have plane 1, 2x minus y plus z minus 1 equals 0, and plane 2, x plus y plus z minus 6 is equal to 0. Okay. There we go. That was maybe a little dark. Let's eliminate one variable. So I've got a lot of choices when I'm looking at this and doing elimination. I could multiply equation 2 by 2 and then subtract them and eliminate the x's. I could just add equation 1 to equation 2, and then magically when I do that, the y is going to disappear. If I subtract equation 2 from equation 1, I'm going to make the z disappear. And that might be all right too. But what am I going to do? I am going to do equation 1 minus equation 2. And so I have chosen to eliminate z. Okay, so 2x minus x is x. Negative y, subtract positive y, is negative 2y. Z minus z is 0. Ha ha, got rid of it. And negative 1 minus negative 6 is positive 5. And that is all equal to 0. Okay. So when we're looking at the intersection of two planes, this is pretty much as far as we can eliminate things. And what we really want is we want one of those equations of a line, like a parametric form. So here's what I'm going to do. I'm going to let y equal t, and then I'm going to substitute that back into the result here, and I'm going to express x in terms of the parameter t, and then I'm going to find out z in terms of the parameter t. Okay, so here we go. If y is t, then x minus 2t plus 5 equals 0. So x is equal to 2t minus 5. There we go. This is starting to look more like that parametric expression of the equation. I've got y equals t, x is equal to 2t minus 5. Finally, I'm just going to substitute these values for t into here, and I'm going to come up with an expression for z in terms of t. Okay, so x is 2t minus 5. I'm going to use equation 2 because it's just going to be easier. Equation 1, I'd have to multiply by some of the coefficients. So there's x, and then y, well, that's just t. Z, we don't have that one figured out yet. Minus 6 is equal to 0. And so let's gather up some like terms. 3t minus 11 plus z is equal to 0. So z is equal to 11 minus 3t. So there's my parametric expression for z. There's my parametric expression for y. And there's my, x. And there's my parametric expression for y. Hence, I've got the equation of a line. So I have found the line of intersection of these two planes. One thing you can check out before you start is you can make sure that the planes are not parallel by looking at the coefficients. Okay, so we know that the normal vector to this plane is 2, negative 1, positive 1. And we know that the normal vector to this plane is 1, 1, 1. If those normal vectors head in the same direction, in other words, we have exactly the same normal vectors, or the more likely scenario, which is that we have normal vectors, one of which is like a scalar multiple of the other, that means the normal vectors are headed in the same direction, and that means the planes are either parallel or coincident. But just taking a look at these, I know that the normal vectors don't head in the same direction, and hence the planes aren't parallel. Okay. Good enough? There's how we find the line in parametric form. We're going to look at a second problem, and it has to do with, we get to use those normal properties of the planes again. So here it is. We're going to find a line that passes through 5, -2, and 3 that is parallel to the intersection of two planes. So plane 1 is given by x plus 2y minus z plus 6 equals 0. So there's my first plane. And pi 2, which is y plus 2z minus 1 equals 0. Okay, so there are my two planes. We want to find a line that's going to pass through 5, -2, 3. And we want it parallel to the intersection of these two planes. All right. Oh boy, here comes the drawing of the intersection of planes. Why did I erase that? There we go. Just not planning in advance. Okay, so when we went through the preamble, we basically saw how the normal property of both these planes relates to the normal property of this line. Okay, so we saw the normal to this plane and the normal to this plane. Both of those normals are perpendicular to this line. And that makes sense. This line is contained in plane 1. It's also contained in plane 2, and it's unique. Since the line is in plane 1, it has to be perpendicular to the normal of plane 1. Since the line is in plane 2, it has to be perpendicular to the normal of plane 2. And so it's perpendicular to both of those normal lines. All right. Haha. So if it's perpendicular to both of those normal lines, then it's going to be perpendicular to the normals. And we have a formula that tells us a line that's perpendicular to two vectors called the cross product. Okay, so normal vector 1 is 1, 2, -1. So that is normal to the first plane. Normal vector 2 is 0, 1, 2. So there are my two normal vectors to this plane. And I want to find a vector that's perpendicular to those normal vectors, and that's going to tell me the direction of this line. And so I'm going to do it by finding the cross product of n1 by n2. And so I'm going to do my cross product formula setup here and hopefully not make too many mistakes. So 1, 2, -1 twice, 0, 1, 2, 0, 1, 2. There we go. Get rid of those guys. Do the cross product. So 4 minus -1 is 5. 0 minus 2 is -2. And 1 minus 2 is -1. So there's my vector that is perpendicular to both of the normals. Oh, this is this is 1 minus 0. Oh, a little bit of peanut gallery stuff there. Turns out it's 1. Okay, might have made a mistake. All right, there's my vector that's normal to both of these normal vectors, perpendicular to both of them. This is going to be my direction vector for the line. All I need now is a position vector for that line, but look, everybody, there's my position vector, 5, -2, 3. And so my line is actually going to be equal to this position vector plus some parameter times the direction vector. There we go. So we've used a couple of our tools. We've used our cross product, which tells us the perpendicular to two vectors. And we've used the normal property of the planes in order to find the direction vector. We were given a point that line passes through that was parallel. So that was a little bit handy. Otherwise, we might have to find out a place where the line is. All right, so that is the intersection of two planes. So tomorrow we go on to the intersection of three planes.